Thank you, Casper.
Very good. Good evening, everyone, and thank you and welcome to this fourth edition of the AI4Health Chair. We move on from a very exciting European AI Week where we had more than 13 events focused on health, and we move on with a new event for the AI4Health Chair with aims at showcasing the best practices and the most promising projects around AI in healthcare that really improve patient care. And for the fourth edition of this AI4Health Chair, I wanted to invite a very interesting speaker. I wanted to talk about in this AI4Health Chair about surgery, which is, of course, a very special field of medicine, one that many people rely on, and how AI is impacting that field. And for this, I invited Dr. Peter de Backer, who is with us today and will present the field of AI in surgery. Peter is a civil engineer and a medical doctor, so he knows both fields, AI and health. He has a passion for new medical technologies. He went from studying biomedical engineering and microelectronics to studying medicine and having a time in surgery. And afterwards, this 3 years in general surgery and urology, well, he went on into researching AI applications in surgery. And as such, Peter leads the surgical field and the Orsi Innotech department at Orsi Academy. Orsi Academy is one of the world's largest training centers in robotic surgery, which is situated near Ghent and is one of our Belgian pearls of technology and health. So Peter leads this Orsi Innotech department, and where he tries to bridge the technological gap between medicine and engineering through innovation. And Dr. de Backer, the floor is yours. Amaze us.
Okay, thank you very much, Giovanni, for the very kind introduction. So I'm quickly going to share the screen and then we should be ready to go. Right, okay. So as Giovanni already explained or elaborated upon, I'm responsible for the Innotech department at Orsi, which is a training center for robotic or minimal invasive surgery. So Orsi Academy, what we do is we train and we validate minimal invasive surgical technologies, and we do this from a really basic point of view in which we validate every step of surgical training and show, as is very important in medicine, that training that we perform or that we give, that it is evidence-based. So to start off with a quote, I wanted to start off with this quote is Claude Shannon, who is considered the father of information theory, said some probably 50 years ago that he visualizes a time where we will be to humans, to robots, what dogs are to humans, and he's rooting for the machine. So what I'll go through in my talk is showing you that this is really not the case and that we shouldn't be afraid of robots or artificial intelligence and what the state of the art is at the moment. So current state in robotic surgery, here you see Andrew. Andrew Ng is one of the major speakers or teachers in artificial intelligence. So if you want to really learn about this field or start from scratch, this is really the guy you should follow and follow his free or available courses on Coursera. So Andrew undergoes a CT scan, and what you see in a CT scan is, I already made some colors in the scan, but in yellow you see a big renal tumor. So he has a large tumor in his right kidney, and what Andrew really needs is a partial nephrectomy, meaning that in surgery you remove part of the kidney, but you leave the kidney, the healthy part, in place. Okay, so robot assisted, what does this mean? This means that you do this with this very special machine, which is called a surgical robot. Here you see a system of the largest shareholder in that market, which is Intuitive. And basically you have, let me see if I can get a pointer. Like this, you see a surgeon sitting and he's remotely operating these arms or these instruments, which are then put inside the body of a patient who is lying on this operating table. And here you see an assistant who is helping him if he needs to switch instruments or if he needs something else inside the abdomen to make this possible. So it's really a master-slave correlation in which the robot blindly follows what the surgeon does. So there is no artificial intelligence involved. It's just master slave, and without the surgeon, there is no robotic surgery. Okay. So surgical planning, then, if you have this tumor and you have a scan like this, it is clear that if you have something like this to base your surgery upon, or you get a 3D model like here on the right side, you can see a tumor here inside. You see how these vessels go, vessels that are not from the kidney that just pass anteriorly, how this facilitates the understanding of your anatomy. And this is basically the first part in which artificial intelligence comes in. This is the surgical planning. Later on, I will elaborate on how it helps in the workflow and how it helps in the performance and the analytics of the operating theater. But this is really the basic where everything starts. You have a surgery and you want to do the surgery. What we developed here is something that builds upon these 3D models, and this is something we have been developing at Orsi together with some of our great partners and clinicians. Is a tool in which you can preoperatively plan which part of the kidney you want to tackle. So you see a tumor here, and then you can see, look, which vessel would I need to tackle to really edit or attack that particular vessel, so that I can remove the full tumor, but do nothing with the actual healthy tissue, so that you don't have ischemic or healthy zones deprived from oxygen-rich good blood. And this is how this can help surgery. Does this mean that nowadays you have these 3D models everywhere? No, not at all. These 3D models are very expensive. Here you see a surgeon who's doing, who's making a 3D model. He needs to do this after his surgery. He doesn't really have a lot of time because he's doing a lot of surgery, and the packages or the software that do this are very, very, very expensive. So this is why these 3D models are not generally used in medicine, and that there is also quite little evidence on these 3D models on how they impact or benefit surgery. The reason that this is so difficult, here you see how this 3D model is being made. So this is a link between surgery and radiology. This is where you go towards the CT scan of your patient and you color in all different parts of the tumor, of the kidney, of the vasculature. And you start to get, if you do this, you start to get a full 3D model of the kidney. But this process easily takes up to 1.5 hours, 2 hours. So it's very, very time consuming. All right. So if you say that this is time consuming and that it's a repetitive task, that's where artificial intelligence, of course, comes in. So here on top, you see a model that we made in 3D, fully manual. You see the tumor, you see the kidney, you see the oxygen low blood coming back. You see the oxygen rich blood coming back here, going into the kidney here. And you see here the system that's fully automatically, so without any labor, is being generated. So of course, when this 3D model is automatically generated and you only need to add some minor details at the end, like the small branches here, you win a lot of time and these 3D models suddenly become economically feasible. And if you then look inside these CT scans, you see that if you compare top and bottom, they're actually quite similar. You would say on the top here, they're not too similar. But if you look inside the CT scan, I don't know if there's any radiologist in the audience, you would see that they're actually quite well. So what we have is 3D models everywhere with a happy surgeon and a low cost. So this is really where we are aiming for, right? So this is how this comes in. How does this work? I will briefly touch upon that, but not too long. A lot of the research that's been done there uses 3D units. And basically what this does is it compresses the full CT to the essence of what you want to detect. And then it expands this essence that you detected, it expands this to the full CT once more. But what it does is it filters the necessity of what is really you're trying to detect, but you pass through your own CT with some information so that you make a very reliable detection. Maybe you have heard about the essence of data. You need a lot of data to do artificial intelligence. And that's very true. In computer vision is what we focus on mostly in surgery. This is equally true. One way to do this in this case is called data augmentation. So here you see a CT scan of a kidney, the original one. You colored in this one, but if you flip it, of course, there's also a kidney on the left side. There's no liver, but still it allows you to do some artificial generation of data. You can put some noise on it, as you can see in a CT scan sometimes as well. There's some noise because the images are not too crisp, and you can make it a bit thinner or a bit more round, as you can also see in the natural variation of our population. So we now know the 3D model, and this is something that I saw earlier. So this type of robots, they do fully automatically. If you give them a 3D model, they fully automatically do whatever you instruct them to do. It's very precise, it's very fast. In this case, they're making a carriage for a baby. But what is happening here is it gives you the idea that there is nothing that you cannot solve with robotics nowadays. So why is surgery not automated yet? If you if you know about these 3D models. And this is what the second part of the talk goes about, is your robotic surgeon will see you now. If we look at the automation of surgery or the different steps, you see that there is a part of no autonomy up until the full automation. And the point where we are at now is this one here. For soft tissue, meaning operations on bowel, on kidney, on bladder, on liver, on lungs, on cardiac, on brain partially, there's no autonomy. If you then go towards orthopedics here, what you see is that in orthopedics, there is already some task autonomy. And one of the reasons for that is that the drilling that you saw earlier, this is the type of operations that's being done inside with the human body. When, for instance, they place a knee prosthesis, they need to cut automatically, and you know where you can cut. So this is the part where this is easily transferable. If you're doing robot-assisted surgery inside your abdominal cavity or inside your chest, you have very little space to put in a robot that can do all of this drilling automatically. So this is why this is a lot more difficult. If we then, of course, however, look towards soft tissue research, we see that we are already in the third phase. And to give you an idea of where this field is going and where we are, this is a very advanced group of UC San Diego in California, where you see that they designed a system where this robotic arm, which is a suction device, automatically detects where the bleeding is coming from and automatically goes towards the point where this suction is derived from. So you see that this is really where the bleeding comes from, and it automatically is able to detect and to assist the surgeon in his operation. So we have two challenges to tackle. We need to steer the robot, and we need to know what is going on in the surgical field. So if we talk about steering the robot, you see that basically, should you theoretically know where the needle is and you steer a robot right through it, this is not going very successfully. Here you see the grasper is completely grasping behind where the needle is. Same point for the right, for the peg. He's not taking the items he should be taking, although he knows where the item is, okay? One reason for this is in robotic surgery, you have these hinges, a lot of hinges with just easy tendons. So if you move them, the wires that pull these is like a puppet that you can move with wires. These wires get strained, they are used a lot, they are reused about 10 to 20 times. So the precision the precision is not always the same, and there is some variation in the way they work, and you're not completely sure where your instrument is. In classical laparoscopy, which is very often used nowadays, you don't have this. But these are the type of instruments that you cannot steer automatically. But this is the reason why this robot grasps where he should not be grasping. So this group, they did a really smart thing. They calibrated this robot with all types of sensors. And what they saw is when they steer the robot and they try to check where the position of the robot is that when they look at the different parts of the instrument, so you have the elbow, you have the wrist, you have the point where it's moving, the further you move towards the tip, the more the deviation becomes, because there's so many combinations of directions that it's no longer very precise. And this is what you see in these curves. The point where it should be going, or the point where it really is really deviating. And this is why it's very difficult to steer the robot automatically. So what they did is, of course, they used artificial intelligence to tackle such a difficult problem. And what you see here is they use a type which is called the recurrent neural network. This is a type of deep learning. If anybody wants to know more about it, feel free to reach out. What they did is they put in this uncertainty and they trained the model to cope with this uncertainty of these different hinges. And you see now that it's able to very precisely grasp where it is going or where it should be going. So this means that the success rate is improved from 40% to 96%. And if you then train your both robotic arms on this transferring, what you get is a superhuman performance. So basically here you see what a surgeon has been doing, here you see what the robot has been doing, and then you see that this robot, he makes almost no errors. You see, compared to the surgeon and compared to the beginner, of course, the surgeon is a lot better than the beginner, but the robot has no variation, he has no standard deviation, and he's always doing the right thing. And you see it here as well, he can easily transfer from one arm to the other one and just move. You also see these flashes, which means that the robot does not know where the items are in space. He knows how to approach them with this neural network, but he does not know where they are in space. So basically, you could say that we've tackled the part in which we want to steer the robot automatically, but we still do not know where these instruments are moving. Okay? So this is where instrument detection comes in. And this is some work we've been doing at Orsi Academy. Here you see some automated detection of instruments. We also do this live. So here I'm doing a partial nephrectomy on this pig here. And you see that we are lively tracking and locating where these instruments are, how they are moving and whatnot. And you can see that this becomes very relevant. You should say why. I will come to that very briefly. But here you see that this does not only work for robotic instruments. Here you see a demo of a commercial package in which they are able to just do the exact same thing in open surgery with suturing, with needle drivers, with pens, with here the needle driver. So you're able to do this on a lot of applications. If you then detect where these instruments are and you combine this with 3D models, you're able to really make a GPS for your surgery. Here you see the kidney model projected on top of your surgery. And then, of course, if you know where the instrument is moving, you can make this very, very precise. Next step, if we are training people, you can see how these instruments here, they are moving and these instruments are tracked, and you can see the patterns that the student is making while he's doing the surgery. And then you can compare, for instance, patterns of people who have never done surgery before their training, and then after their training. And we can derive all sorts of factors from it that might give us an indication on how good somebody might be, which is something that we are heavily researching, but which is something completely different from our patented methodology, which is called proficiency-based progression. Happy to elaborate on that in another setting, but I'll leave it for now. So when you have these instruments and you have all of these instruments detected automatically over the time frame of your surgery, you see that you see a surgical fingerprint that emerges. And here you see, for instance, for a certain procedure, when the tumor is being excised, you see that there are certain clips starting to come in. So when you need to close, this is again, so I put the whole talk around kidney surgery to make it more uniform. But here you see these clips coming in, and you see that this is a certain part of the surgery. And you see how these patterns are very specific per surgery, and you can derive all types of information from that. If you have a young surgeon or a very expert surgeon, they can compare their patterns and they can check, okay, what am I seeing? What can I learn from him? I'm doing a lot of instrument switches. This is our CEO, Alex Motri. He's a very, very, very good surgeon. And he does this surgery. He uses constant suction. Maybe I use too little suction. He uses this, he's a lot faster than I am. He uses certain instruments in certain directions that I should be using, and I can learn from him. But he can also learn from other experts, and other experts can learn from him because they will have other parameters that are differentiating them, and they can learn from each other as well. Here you see some very nice work from the group of Strasbourg, and what they did is they automatically detect these phases based on the instruments that you see for gallbladder removal. So here you see a typical laparoscopic surgery, so not robotically. and they automatically switch between the phases, and they detect which part of the surgery the surgery is in. And why is this important? Well, if the surgeon can work fluently because the nurse knows which instruments will be needed in the next phase of the surgery, the assistant knows what job he needs to do, and the anesthesiologist knows how long the surgery will remain or how far we are in the surgery, so she or he can adapt her or his opioids or her analgesics towards that surgery. So this is why this is very important. Now, what do we need to do to make this vision possible? It's clear that there is some very, very large challenges to tackle in this vision part. We need to collaborate. And this is really what I wanted to state is if we want to really progress this field, we should share best practices. We should think about how we can share our data sets. And if we do that, I really, really believe that the AI will not replace the surgeon, but it will perfect your surgery. So surgeons should not be afraid about artificial intelligence because it will enable them to do more precise surgery, to learn a lot better, and really to go towards perfection. And I think this is where the field of AI can help us in surgery, but I'm quite sure that this, or at least I'm very convinced that this will be the same case for every part of medicine. So thank you very much. And if there's any questions, I'm happy to take them.
Thank you so much, Dr. De Backer, for this very nice presentation of AI in surgery. While the questions maybe come in, and they may come from YouTube, from Zoom, from very different platforms in which we are streaming this event, I want to start by asking you this question. Outside pure research project, do you know of any hospital in Belgium, or do you know of any department, even outside Belgium, that is actually using, for instance, image detection or any other data augmentation processes that you describe? Yeah.
So first of all, these projects, they are still very infant. So to get these medically certified, to really use them on a daily basis, that's nearly impossible at present. However, I showed some images of the group of Strasbourg. They have a very large data science lab in which they try to do some tests or some demos on how this works or how this can help surgery in medical trials. And that's what we also have at ORCI. We have medical trials ongoing in which we really check during surgery, how is this going, or how is this safe, or what can it do, or what can it not do, where explainability, for instance, is very, very crucial. There are some companies who are going into this field. For instance, Medtronic has launched a new robot about 3 months ago in Europe, at least. And they have a platform that exactly tries to do this. It's also very at its infancy because there's plenty of challenges to be tackled. One surgery is not the other surgery. It's not that simple to transfer the findings. And there are some other small companies, like I showed the open surgery as well, that do trials, but they are more providing post-operative analytics on the surgery rather than intraoperative assistance. So it's more like in the field of radiology, they're quite more advanced. You have these algorithms that already triage up front or tell you which CT scans you should look up front. This is not the case in surgery yet. It's not diagnostic. It's more reflective at the moment of how you can do better or where you should improve. So we're definitely lagging behind on all other fields. And this is why we should really focus on getting everything together. And I'm also happy to speak for the AI4Health chair, because I think as a Belgians all together, this is something we should really try and achieve.
Absolutely, Peter, and this is why it's really interesting that we should start in the AI4Belgium in close collaboration with ORCI Academy and all the different stakeholders, dedicated surgical task forces. And I see you well positioned to lead such a task force. I have a question that comes from your recent answers. Okay, these projects are infant, but we as Belgians, we can put together our best surgeons, our best surgical centers, the ORCE Academy, AI4Health, and start some big projects applying this surgical AI in clinical practice. Let's imagine that one AI product in surgery comes on the other end of the development process and gets to be commercialized, say by a major stakeholder. The difficulty that hospitals see nowadays in the adoption of AI, aside from the implementation part, is the actual financing that comes from buying AI technology. Have you asked yourself the question, how should surgical AIs be financed? Should the Belgian federal state come up with a reimbursement plan for using one or two given AIs per context, or should hospitals invest in them because it will reduce the reopening of patients, or the what is your thought on that?
So I think the government has a very, very important role to play in this. Likewise, in everything that we try to do in medicine is, if you want to collect the data, first of all, there is no uniform system. There is no uniform electronic records, which is something that I think is reoccurring in every conference, etc. If you want to really take things forward quickly or massively, I think the government should decide on a platform that should be used in every hospital. And this is, of course, where the free market comes in and where it becomes very difficult to really get one platform everywhere. And this is actually what should also happen in surgery. There should be one guideline, and you should know that the largest communities worldwide in surgery, the largest conferences, they have no consensus. They have working groups now trying to get consensus on what should be a good surgical video or what should be a good annotation. It's not like we know how it's done. We're really trying to understand how it should be done. But if you can, at least on a national level, get some guidelines and say, look, this is how you need to prepare data, or look, this is what you can do with videos. We have a lot of surgeons coming to us with the same problems or trying to push this field forward, but there is no framework to do so. So at ORCE, we try to build a framework and push it forward and trying to explore what can we do medically, legally, what can this mean for the surgeon? Because this is really a very, I think this is very important that the government takes a stand or really tries to shape this so that we know how we can build this as a community, so that we also do not face the possible danger of everything going into the big companies that are now trying to fish everywhere and to get every hospital to give some data and to go to and to collab and to get a dispersion of data, rather than making one force together and trying to combine everything together. So there's definitely an important role for the government there. Second part is, of course, who should pay for it. I think, first of all, there's a lot of good funding and opportunities from Europe that try to push this field, where healthcare is always one of the key important factors. So I think there's definitely support from there. And I think we also already have a good amount of knowledge in Belgium as such. So I think from a cost perspective, this could be really quite okay, and it shouldn't always be very expensive to do AI. There's plenty of ways to make it cost efficient, but collaboration is key.
That's really key, of course, and the topic of the role of the government. So one of the outcomes, for instance, for the surgical task force could be to propose to the authorities one framework, one guideline, one document that we could use to encompass, to accompany the development of surgical AI in Belgium. And this could be the goal. And for the first part of what you said about data structures in Belgium, things are coming forward. We will build in 2022 one coordinated platform. Belgium will have a coordinated platform for all data that comes from patients. And with the advent of the Health Data Authority, with all other initiatives, things will come together. I'm very hopeful about that. But as you say, guidelines should be published, guidelines should be adopted. And the federal state should accompany the use of surgical AI from development to adoption and implementation, of course. And this is one key message. Very good. We have a question from Professor Olivier Lemoine from Université Libre de Bruxelles, Hôpital Erasme, who says, do you have any additional examples outside the field of laparoscopic surgery? And he talks about, do you have some example in therapeutic endoscopy, such as GI, urology, pulmonology?
Yeah. This is exactly the same challenges that you need to tackle, right? We have some projects in which we do detection in endoscopic images. And there are some very also openly available large data sets there, for instance, in polyp detection. In general, in colonoscopy, where you look and when everybody can have a bad day or a long call, and you're less attentive during the colonoscopy and you miss a polyp, and where these systems are already live, there are systems now that assist really this detection during surgery, but this is really like detection. So when I said earlier that these systems are really in a prototyping phase, these are indeed the types of systems where you already have some decision support. However, I don't dare to say anything about how far they are in the medical certification or how precise they are, but I know that there are very far ongoing trials in really enhancing polyp detection, for instance, in colonoscopy. Or there are other trials, the same lies in urology. When you do endoscopy, you also have polyps in the bladder, for instance, where they try and detect or look, this zone is a bit suspicious. Is it red, or is it carcinoma in situ, or is it just inflammation because of some installations, or what is it and what could it be? And this as well, it can be very, very useful for young doctors. For the same thing for myself and for some of my colleagues who are taking their first steps in surgery. If you have a system that has seen millions of cases behind your back and you're doubtful and you're alone in the middle of the night and you can check that system, it might help you to make a better decision than when you didn't have that decision. Even though if it's only 95% sure, you will still do a better job than most of the semi-experts or the people who have some career already. So I think that these are the types of systems that will probably hit the market first, like some semi-supportive systems that don't make the decision for you, but will give you support in making, did you think about that? Do you know that this is can also be this type of lesion? And that this is where purely detection can help.
Very good. Amazing. Okay. I see no other question, and I see that Professor Lemoine is very satisfied with the answer that you just gave. I see many chiefs of departments, many professors around different universities that are connected today, which is a very good thing. This means that this topic is of interest and we can move forward. So let us move forward. Dr. De Backer, thank you so much for this amazing presentation. I want to call on the public to reach out to Dr. De Backer if you have any questions. Reach out to me if you have any questions for any other previous AI4Health chair. I want to announce that ULB, Université de Bruxelles, and University of Mons will launch in September 2022, the very first university certificate in artificial intelligence in medicine and digital health. Dr. De Backer will be one of our speakers in the certificate. And I invite you to get in touch if you want to pursue this kind of education. And I invite you to the next chair, AI4Health chair, who will take place in the month of May, on the 19th of May, and we'll tackle some very interesting use cases of data analytics and AI in healthcare. Thank you so much once again, Dr. De Backer. Thank you so much, Casper from Tech Support and BOZA. And thank you to all of you for participating into this AI4Health share, whether on Zoom, on YouTube, or any other platforms that BOZA has offered us today. See you next time. Bye-bye.
Take care. Bye-bye.